right, we are back, and as I said, the last video, from here we'll start to discuss about articulated joints, and with this topic, um, is kind of a entry to start to discuss about Danovic Hartenberg representations. And on this video, as I'm using the third edition in English, so on this edition, if you have the opportunity to follow using this edition, you notice that the topic 2.10.3 is a very short topic, and it's just bringing the subject about articulated joints. But this is something that we discuss when we are discussing about Danovic Hartenberg. Okay, and what this topic is telling to us is very simple, very short. And I'm basically will write what is being said on the book. So articulated joints. And of course, I will give you examples of articulated joints. And um, starting with Danovic Hartenberg, we already got a very nice example, a figure illustrating three joints connected by two links, and the explanation of this model. Okay, so articulated joints consist of three rotations other than RPY or Euler. And this is all that this topic is bringing. And as a complement, we can even try to do a illustration and using these rotations. Okay, so we have this articulated robot. So when you heard articulated, you automatically it has to associate to joints. And we have these links right here, another joint, another link, and on the end effector a tool to make to perform a certain task. It can be a hand to grab a object, It can be a camera to record something, and all this is going to depend of the task that this robot is being selected to perform. Okay, and of course, we need to attach to this robot frames so we can track its motion all the time, and also to be able to program this robot to pass coordinates to it. This is something that we are seeing since the beginning of this series. So we need to have this frame as reference. So we do rotations. We have three rotations, specifically on this unarticulated robots. Right here, we can do a rotation. So this rotation is being done above the z-axis. Right here, we can do also a rotation, and now it's more easy with if we attach it a imaginary frame, like if he's pointing outside of the screen, so we can, because it is exactly the axis in which we are trying, not trying, but really doing this transformation. So the transformation that we are doing with this data 2 is a transformation above or around the axis that is pointing outside of the screen. So with something like that. And let's say that is, I don't know, maybe Y, and this is X. Something of this nature. And right here, the same thing. Let me place this right here. A third rotation, again, a imaginary frame. So this is a frame, is a reference frame, and let's say this is Y. Okay, and again, something that we are doing since the beginning of this series. We have this vector, and we name this vector as P. And right here also we have this reference frame, this moving frame. E, N, and O. So remember that these frames we represent uh, with a matrix. So the initial position and the orientation in which these frames are located on a space, we can represent with coordinates using matrix. So the elements of the matrix, they are coordinates. And as we are using this, now let me name this. This is also a reference, but also the moving frame. So, and something that from here you might to be able, you have to notice that this frame is a reference to this frame, and like I've been said all this time, and I keep repeating, just because of this we can write transformations. So if we name this, again repeating the same situation, if we name this as a hand, so it's the hand of the robot, and right here is the reference. Of course we have our own universe reference frame. And we can write a transformation, something like that, a transformation of the H frame in relation to the R frame. And what I wanted to comment with you, because of this, as this moving frame are being referenced to this R frame, so we have this matrix exactly shape on this system of coordinates. So we have n because of this n, and we have x because of this x. So we have nx, we have ny, we have nz, and right here 0, because this is we are trying to maintain this matrix on its quadratic form, and also this is the scale factor, of course, the debut. We have OX and O because of this axis, O. So OY, OZ, 0, AX, AY, AZ, 0. So A because of this axis, and X because of this x-axis, Y because of this y-axis. You understand? So because of this reference frame in this moving frame, we got this matrix with this shape made for this coordinate system. And because of this, we can write these transformations, we can write transformation equations, we can track the motion of this robot, and this is for the orientation. And this last column is for the position, so px, py, pz, and 1. And if right now we apply, let's say for px, any of these angles of rotations, theta 1, theta 2, and I forgot to write right here to draw theta 3. And right now we can do a decomposition of this p vector. So decomposing this p vector in sine and cosine components. So px times cosine of theta, or p times cosine of theta, which is px, and p sine of theta, which is py, something like that. Okay, so this is all that this topic is bringing, and for me it looks like a revision, and this is why um, it jumps to the topic 2.11, and it is also kind of telling something that it was already worked, which is forward and inverse kinematic equations. So forward and inverse kinematic equations. Position and orientation. And we know that forward and inverse kinematic equations, we know what they do, which is exactly allow us to do a analysis of the position and the orientation of the robot, of the factor of a actuator. So if we are interested on the position of some robot, we apply the forward kinematic equation, and if you are interested in the orientation of this robot, where the joints it will be, where we want to put these joints, how we wanted to orientate this robot, so we apply the inverse. So both of these equations, they work together. So if you remember, in order to analyze the orientation and position of a robot, um, we use inverse transformations, so we kind of reduce a transformation equation, and after this we use the its matrices, so we can know where is going to where which is the final position and orientation of this robot, of this end effector. And again, I will just use the content of the book. This is very short, so I'm not seeing any problem with this. So we know that the matrix that represent the final position and orientation of the robot is a combination of positioning, choice, and an orientation choice. And this is basically what I have just explained to you, the reason why we use part in inverse kinematic equations. Um, so the same which is being said on the book, we are capable of do a analysis of the initial position and orientation, and also the future position and orientation, since we can apply these inverse transformations. It's not something so intuitive, and if we go back and use a example, so let me try to find a example in which we have applied forward and inverse kinematic equations. So we were able, I think right here we are applying this inverse transformation, but I wanted to find some that we reduce the transformation equation right here. This one I think uh, we can use as an example. So let's see. Or we can even find some more, a example more simple. Right here. Let me see. No. Maybe this example on the topic 2.15. If you remember, we were doing this example in which we have a camera attached on the end effector, and in order to know the final position and orientation of this camera referenced to this object, we use inverse transformations, as you can see. So this is the inverse transformation of the H frame in relation to the 50 frame. And this way we are able to reduce this first transformation equation, and we obtain this one, and we apply more properties, and we were left with this one. And after this, passing now to this made this equation to this matrix form. So instead of use these transformations, we are using now matrices, and this way we are able to find this final position and orientation. So when we are talking about forward and inverse kinematic equations, you automatically need to relate to the use of inverse transformations. So is a way to do this analysis of the motion of the robot. Where is it, the initial position, and where we wanted to put it. So the final position of our choice, like it's being said right here. So it continues now give it to us giving a example. So example, if right now if we have a Cartesian plus RPY robot, Cartesian and RPY robot, its final position the final position and orientation of the end frame and on the end frame, of course, we got the end effector is given by, so just like we have done right here, we have reading this transformation, so we can even use this illustration to complement this example. So the transformation of the H frame in relation to the R frame. So this means the final position and orientation of the, not just the end frame, but also the end effector. So on the end effector, we got this imaginary end frame attached. This moving frame, sorry, the moving frame. So of course, the final position and orientation of the moving frame is the final position and orientation in which this frame will be localized. So is the transformation that is being occurring on this Cartesian coordinate system. So Px, Py, and Pz. And as this a junction of the RPy as well. So we got this, the RPy matrix. And just like we have done right here for a coordinate system like the spherical one, and now using the Euler angles. So another example, it will be a spherical and Euler robot. So for its final position and orientation, which is being represented by this transformation. So we are doing again a transformation of this H frame in relation to this R frame. And right now the transformations are occurring on the spherical coordinate system. So we got this R translation and the beta and the gamma rotations and the Euler matrix being applied with the Euler angles. Okay, so Dynavit-Hartenberg, which is the next topic, is what we call the standard way of representing robots and modeling their motions, and therefore is essential to learn. And this is the words of the book. So till here, we saw how to do these representations using this coordinate system, the Cartesian, the cylindrical, the spherical, and instead, right now, instead of use these coordinate systems, we use the Dynavit-Hartenberg representation to modulate these robots. So on the next video, we will start to discuss about Dynavit-Hartenberg. So Dynavit-Hartenberg representation of forward and kinematic equations. Of robots. Which is basically a method of representation and a way to modeling robot links and joints of any configuration. So I have already done this sketch, so let me just use it. Okay, so we can start our discussion um, about this topic on the next video. Um, from now, it's all, and hope you enjoy it. And thank you.